Hi everyone, today at the seminar we are hosting Aida Mousavifar. Aida, please start.
So hi everyone, I will talk about a spectral graph clustering in sublinear time. This is joint work with Greg Guluch, Michael Kapralov, Silvio Latanzi, and Christian Sohler. So this talk is about graph clustering. We assume that we are given a graph and we want to partition the vertex set of the graph into k non-overlapping sets, C1 through Ck, that they look like communities or clusters. For example, for the graph in the slide, a partition into 3 clusters, C1, C2, and C3 is a pretty reasonable solution. And clustering is a basic primitive in graph analysis, and it has many applications. For example, when you want to find communities in social networks. In this talk, we are interested in the following question. We are given a graph that can be partitioned into k good clusters, and we want a very fast algorithm or sublinear algorithm that let us recover every cluster with high precision. So now a natural question would be, what is the definition of good cluster? We assume that our graph is deregular. Therefore, any induced subgraph C or cluster C, and then for any cut S inside C, we define the conductance of cut S with respect to C as the number of edges crossed this cut, normalized by the volume of the smaller side of the cut. And we quantify the notion of good cluster by conductance. So, and intuitively for us, a good cluster is something that is internally well collected and has a sparse cut or a sparse boundary to the outside. So now with this notation in place, I define the inner conductance of a cluster as the minimum conductance over all the cuts inside the cluster, and I define the outer conductance of a cluster as the fraction of outgoing edges normalized by the volume of the cluster. So then for us, a valid cluster is a vertex-induced subgraph that has large inner conductance or internally well connected and a small outer conductance, which means that it has a sparse boundary. So we say that a valid cluster is a vertex-induced subgraph with inner conductance lower bounded by some parameter phi in and outer conductance upper bounded by phi out. So an inner conductance is related to many fundamental properties of your cluster. For example, it's related to the eigenvalues of the normalized Laplacian to Ricci-Gerz inequality. Or if you have a cluster that has inner conductance lower bounded phi in, we can show that the random walks mix in time roughly 1 over phi n squared times log n. And this will be important for our analysis later. So now, given we know the definition of good cluster, I can tell you what the problem we are solving is. We say that, and the goal is that we have a graph that is somehow clusterable, and we want to recover these clusters perfectly. So now let's define what is a clusterable graph. We say that graph G is k phi in and phi out clusterable if there exists a partition of vertex set of G into k non-overlapping sets, C1 through Ck, such that all these k clusters have roughly the same size, say roughly omega n by k, and all of them are internally well connected and have a sparse boundary. So we say that the inner conductance of each cluster is lower bounded by phi in, and outer conductance of all the clusters is upper bounded by phi out. So to simplify the notation for the talk, I will assume that I will substitute phi in by a constant, and I will call phi out to be epsilon. So it means that our graph is a union of k expanders with outer conductance bounded by epsilon. So now I can tell you what is the problem. We assume that the input graph is k clusterable. It means that it's union of k expanders with outer conductance by epsilon, bounded by epsilon. And then our goal is to design a small space data structure that can classify points according to the cluster they belong to in sublinear time. More formally, we want to design a local computation algorithm that misclassify only epsilon fraction of the vertices on every cluster. And note that this is an important feature that we want to misclassify epsilon fraction on every cluster, as opposed to epsilon fraction of the vertices in total. Because, for example, if you want to misclassify epsilon fraction of the vertices in total, even you can return less than k clusters, and that might be fine. But here it is important to output exactly k clusters such that each of them has good overlap with the corresponding cluster. So it means that we want to find k candidate clusters, C1 hat to Ck hat, such that the symmetric difference between each candidate cluster and the corresponding cluster is at most epsilon fraction of the size of the cluster. And also for any vertex in the graph, we want to identify the candidate cluster this vertex belongs to in sublinear time. We refer to this problem as a spectral clustering oracle.
I have a question. So this sublinear refers to preprocessing time or to query time?
Both. We would like to first preprocess the whole graph in sublinear time. Then for any vertex, if someone asks who is the cluster this vertex belongs to, we want to answer that question also in sublinear time. And also another important feature of our problem is that although we would like to answer this question in sublinear time, although you want to know the label of vertex, the cluster of vertex X in sublinear time, if you are interested to know this label for all the vertices, if someone is interested to basically cluster the whole graph, you don't want that the total runtime be more than n. Like you still want to be able to cluster the whole vertices in nearly linear time, but still we want to be able to classify the vertex, each vertex in sublinear time. So now I will tell you about the exact runtimes later when I'm talking about the main results. So but the problem is clear. Okay, awesome. So maybe let's first look at some prior results that have been developed for this problem. Lee, Cannon, and Travison have developed multi-way Cheeger inequalities, and they show that when the outer conductance is smaller than 1 over poly k, then they can output k clusters with outer conductance at most k squared times the square root of epsilon. So I note that this becomes non-trivial only if the outer conductance epsilon is smaller than 1 over poly k. Then CNOP designed an algorithm that can misclassify square root of epsilon fraction of the vertices on every cluster when the outer conductance is a small constant. And note that both of these algorithms have nearly linear runtime, although we are interested in the sublinear regime. Then Schumacher and Soller considered this problem in the property testing regime, and they designed an algorithm that can test the number of clusters in time roughly a square root of n when the outer conductance is smaller than 1 over log n. Later, Chiplunkar, Kapralov, Khana, Press, and myself have improved this algorithm for the case that the outer conductance even can be a constant, and we designed an algorithm that can test the number of clusters in time roughly n to the half plus order epsilon. And we also showed that this dependency on epsilon in the exponent is necessary. It means that even for testing the number of clusters, you need to at least pay n to the half plus order epsilon, even for testing the clusters. So this runtime is tight.
If I may ask, so is it always like when you fix the outer conductance, is it always possible to cluster this into like some arbitrary k clusters and still meet the guarantee of this outer conductance?
So we assume that the input graph satisfies this property. We assume actually.
Okay, yeah.
So the final goal is actually to recover the input, but instead the input, even if you recover most of each cluster, we are fine with that.
Okay.
Okay, so these are the main important prior results that have been developed for this problem. And maybe to start to design a sublinear clustering algorithm, let's first see some of the sublinear techniques that have been developed for the property testing version. So one natural approach is to try a spectral partitioning. So for example, one can compute the eigen decomposition of the normalized Laplacian, embed and project the point into a Euclidean space corresponding to the bottom k eigenvectors, and then partition the corresponding point cloud. However, the problem with this approach is that computing eigen decomposition and SVD on very large graph is computationally expensive, and we are interested in designing a sublinear algorithm. So let's see one of the main ideas behind designing sublinear algorithms in the property testing regime first. So let M denote the transition matrix of the lazy random walk in our graph. Then I will choose T to be a large constant times log n to be the length of the random walk that I will run. Then for any vertex x in the graph, I define m to the t times indicator of vertex x as a distribution of t-step random walk started from x. So this means that I have a vertex x, I run random walks of length t from this, and this distribution will nothing but m to the t times x, indicator of vertex x. So one of the main prior results on this problem is a work by Schumacher and Soller from stock 15. So their algorithm is very nice and it works as follows. So they first start by sampling vertices uniformly at random from the graph. And the size of the sample set, size of S, is poly k, with the hope of hitting each cluster at least once. Then they have this set S, and they try to construct a similarity graph on this small set. How do they construct a similarity graph? For any pair of vertices x and y in the similarity graph, they consider the probability distribution of t-step random walk, m to the t times indicator of x and indicator of y, and they compute the L2 norm distance between these two distributions. If the L2 norm distance between these two distributions is small, say smaller than 1/10n, then they add an edge between these two vertices in the similarity graph. And then the final algorithm is very simple. So they declare the graph G to be k clusterable, or the number of clusters is k, if and only if the similarity graph contains at most k clicks. So this is the algorithm, and it's important to note that one can compute the L2 norm distance between probability distribution of walks up to precision roughly 1/n if you run at least a square root of n random walk from each vertex. And this is intuitively because of birthday paradox and collision testing analysis. Like if you run a square root of n random walks from each vertex, you can estimate these L2 norms with very good guarantees. And that's why the whole algorithm has sublinear runtime. So it has like poly k times s square root of n runtime. So let's see when this algorithm works. This algorithm works only if the outer conductance epsilon is much smaller than 1/log n. Think of this as much smaller than 1/length of the walk. This is because in this parameter regime, the random walks are very good proxies for the spectral embedding. So now let's compare this with our setting. And for putting this in perspective, let's consider the following simple instance of the problem. Let's assume that my graph is 3 clusterable. It means that it's a union of 3 expanders with outer conductance bounded by epsilon. Then for any vertex x in the graph, I consider the probability distribution of random walks of length roughly order log n started from these vertices. So I will consider m to the t times indicator of vertex x, that is the probability distribution of random walks. After that, I will project this distribution onto the second and the third eigenvector of the normalized Laplacian. This is a meaningful thing to do because when your graph is 3 clusterable and when the length of the random walk is logarithmic, all the eigenvectors higher than 3 will just exponentially die out. So what actually will be important is only the second and the third eigenvector. Then when you run such experiments, you will see that in the setting of Schumacher-Soller, when outer conductance is much smaller than 1/log n, the probability distribution of random walks still is a very good proxy for the spectral embedding. But in our setting, when the outer conductance is nearly a linear constant, you see that the probability distribution of random walks is a highly distorted version of the spectral embedding. And we need to work in this regime. So this brings us to our approach. And it's also in particular, one can show that no distance no distance thresholding-based algorithm can be made to work in this setting when the outer conductance is nearly a constant. So, and this brings us to our approach. So let's assume that U1 through Un are the eigenvectors of the normalized Laplacian, and lambda 1 through lambda n are the eigenvalues. Again, I consider the probability distribution of random walks, and I project this distribution onto the second and third eigenvector, because all the other eigenvectors will exponentially decay. So it's not too hard to verify that the probability distribution of random walk, when you project this onto the second and the third eigenvector for vertex x, you will get the spectral embedding of vertex x, that is u2 of x and u3 of x, that is distorted by factor 1 minus lambda I to the t. And this is because the random walk transition matrix has the same eigenvector with the normalized Laplacian, although the eigenvalues are given by 1 minus lambda I by 2. So you get the same spectral embedding, but now it is distorted by factor 1 minus lambda I to the t. Now let's more carefully look at the effect of outer conductance epsilon on these distributions. So when our graph is tree-clusterable with outer conductance smaller than epsilon, one can show that by Chigger's inequality, the outer all the eigenvalues smaller than lambda k are smaller than epsilon. So it means that lambda 2 and lambda 3 are smaller than epsilon as well, because the graph was tree-clusterable. So now in the setting of Schumacher-Staller, when epsilon outer conductance is smaller than 1 over log n, then this factor 1 minus lambda to the t is close to a constant, because t length of the random walk is logarithmic, eigenvalues are smaller than 1 over log n, so this distortion is still a constant. And that's why the probability distributions are still very good proxies for the embedding. But in our setting, when outer conductance epsilon is nearly a constant, then this factor of distortion 1 minus lambda to the t can be as small as n to the minus epsilon. And that's why this is a highly distorted version. It means that we need new techniques that let us to remove the distortion coming from the contribution of eigenvalues and access the spectral embedding directly. And that is our first main result. So let's recall that u1 through un were the eigenvectors of the normalized Laplacian. Then for any vertex x in the graph, we define the spectral embedding of vertex x as a vector in Rk whose coordinates are ui of x. So for example, if I construct a n by k matrix whose k columns are the bottom k eigenvectors, then the rows of these matrices are a spectral embedding of vertices. And recall that our goal was to access these spectral embeddings in sublinear time. So I somehow would like to access or find fx in sublinear time. But note that the bottom k eigenvectors are not necessarily unique. For example, if some of the bottom k eigenvalues are the same, fx is not necessarily unique. Although this might be the case, but the eigenspace defined by the bottom k eigenvectors is always unique. This is because when the graph is k-clusterable, there is a gap between the kth and kth plus 1 eigenvalue. So this eigenspace is always unique. So it makes sense to access the spectral embedding using a function that is well defined on this subspace. So a very natural question would be, for example, is it possible to access the dot product between the spectral embeddings in sublinear time? And that is our first main result. We design an algorithm that can approximate the dot product between spectral embeddings in sublinear time. More formally, when the graph is k-clusterable and the outer conductance is smaller than a constant, we can show that we can estimate the dot product between fx and fy for any pair of vertices up to very tiny additive error, roughly gamma by n. And our data structure has sublinear pre-processing time and query time, roughly n to the half plus order epsilon, times polynomial in 1 over gamma. We can also show that the query time can be reduced at the expense of increasing the pre-processing time, as long as the product between the two is roughly n to the 1 plus order epsilon. Again, I want to emphasize that this additive error gamma by n that we get in the estimation of dot product, it's so tiny. And this is because for a typical vertex x in our graph, when the graph is, for typical x in our graph, the L2 norm of a spectral embedding is roughly k by n. And why this is the case? This is because if you construct this n by k matrix whose columns are bottom k eigenvectors, then because these eigenvectors are orthonormal, each column has L2 norm square 1. And because this matrix has n columns and k rows, a typical row has L2 norm square roughly k by n. So again, it means that estimating dot products up to precision gamma by n is very accurate. Then later, for purpose of our graph clustering, it's enough to set gamma to be a small constant. Then using that data structure that led us estimating the dot products, we can design an algorithm for the spectral clustering oracle that classify vertices according to the cluster they belong to in sublinear time. So more formally, when the graph is k-clusterable with outer conductance smaller than 1 over log k, so it's a union of k expanders such that each expander has outer conductance smaller than 1 over log k, we can design a local computation algorithm that misclassifies epsilon log k fraction of the vertices on every cluster. And our algorithm has roughly n to the half plus order epsilon pre-processing time and query time. So again, here also we can reduce the query time at the expense of increasing the pre-processing time, as long as the product between the two is roughly n to the 1 plus order epsilon. And this is a very important feature of our problem, because if one is interested to classify all the vertices in the graph, then this is possible to do in nearly linear time. So if you have any question about the main results, I would be happy to answer that.
Could you repeat how this, like, how do you use this? Well, did you already mention that? How do you use this previous result of approximating the dot product?
So the main idea is actually that we want to do a spectral partitioning. And for doing the spectral partitioning, like when you project the points onto the spectral domain, this is what you see. For example, when your graph is tree clusterable, you will get the point clouds in 2D. Or when your graph, like, you will get pictures like this. So, and then if you are somehow able to get access to these point clouds, your next goal is to partition these point clouds. Like for that, for example, in practice, people use something similar to k-means. And I will like more carefully go over how we actually do this partitioning. Like I will go carefully over how we actually use these dot products to find the clusters. But the intuition is that if you somehow get access to this point cloud in sublinear time, then your next task is to partition them.
Okay, I was under the impression that you said that this is actually hard because they are close to each other, but
yes, exactly. So the thing is that they are, if you look at the probability distribution of random walks, like here, if I have the probability distributions in the right picture, they become very close. And this is because it is not U2 of X and U3 of X, it is not the spectral embedding, but this is the spectral embedding distorted by factor 1 minus lambda to the t. So that's why they become close. If you somehow able to remove this 1 minus lambda to the t and look at U2 and U3 directly, they are not close anymore. Then they are far close that you can use them.
Thanks.
No worries. Okay, so now that the task is, if assuming that we have the sublinear access to the spectral embedding, how we can use them to recover the clusters. And intuitively, the picture looks like this, like they won't be close anymore. But like we need to formally show why that happens. So again, recall that the spectral embedding of a vertex is a vector in Rk whose coordinates are ui of x, where ui's are the bottom k eigenvectors. So my goal was to partition the vertices of a graph, and then if I represent each point with its spectral embedding in the spectral domain, I get point class in R to the k. So these are the points that you can see in the slide, and they form 3 clusters, for example. So then with this notation in place, we define the center of each cluster in the spectral domain as the average of a spectral embedding of all the vertices in that cluster. And for example, here I get mu1, mu2, and mu3 as the center of these 3 clusters, which is the average of a spectral embedding of vertices in that cluster. And it's quite natural to expect that the vertices should be concentrated around their centers. More formally, using a standard bonds in the literature, we can show that when the graph is k-clusterable, with k expanders with outer conductance smaller than epsilon, then for any direction alpha in R to the k, the number of vertices that deviate from their center along each direction is at most epsilon. Like no more than epsilon fraction of the vertices can deviate from their centers along each direction. And using these properties, we can prove natural properties of, using variance bonds, we can prove natural properties about the k-clusterable graphs. For example, we can show that the centers, as you see in the picture, are almost orthogonal. And we hope to use these properties to recover the k-clusters. So from now on, suppose that we know the center of clusters, and we want to recover the vertices belong to that center in sublinear time. And we will later remove this assumption. And recall that our goal is to recover k-candidate clusters, C1 tilde until Ck tilde, such that the symmetric difference between each cluster and the corresponding candidate cluster is at most epsilon fraction of the cluster. So recall that the main tool that I have is that I can compute the dot product between a spectral embedding of vertices. So what would be a natural definition for a candidate cluster? So because I can compute the dot product between a spectral embeddings in sublinear time, a natural definition for a cluster might be all the vertices that they have non-trivial correlation with their centers. So more formally, I define a candidate cluster Ci tilde as all the vertices that their correlation with their center is large. Or if I compute the dot product between a spectral embedding of a vertex and the center of the cluster, this dot product is larger than, say, 0.9 times L2 norm square of the center. And as you see in the picture, these are all the points that are above some hyperplane or towards right of some hyperplane. So using our variance bond, we can show that because at most epsilon fraction of the vertices can deviate from each center along each direction, we can show that at least 1 minus epsilon fraction of the vertices inside one cluster are towards right of that hyperplane. Like we can show that most of the, like 1 minus epsilon fraction of C1, for example, are inside C1 tilde. And also we can show that the cluster centers are almost orthogonal. So this leads to a natural and simple hyperplane carving algorithm. So we first find all the vertices that are non-trivially correlated with center mu1. We call them C1 tilde. Then we find all the vertices that are non-trivially correlated with mu2. We call them C2 tilde, and we proceed so on. So we first remove C1 tilde. Then among the remaining points, we find C2 tilde all the points that are non-trivially correlated with the second center. We remove them, and so on. So this is encouraging, and we can show that each candidate cluster has a small symmetric difference with the corresponding cluster. However, this approach unfortunately doesn't work, and the reason is that we cannot preclude the fact that this candidate cluster might overlap. And to see this, we can look at a hard example. But maybe first, if you have any questions so far, I can answer that. Okay, so go ahead.
I, for one, I'm fine, for example.
Okay, awesome. So let me proceed to look at a hard example. So let's look at this example. And this is an instance of a K-clusterable graph that is consistent with our variance bond. So as you see in the picture, all the vertices in all the clusters are very good concentrated around their centers, except for the last cluster. So all the vertices in C1, C2, and so on are concentrated around the centers, but in the last cluster, assume that half of the vertices are concentrated around their centers, but among the other half, epsilon fraction are deviated towards direction of mu1, epsilon fraction are deviated towards direction of mu2, and so on. So half of them are at the center, but among the other half, epsilon fraction is deviated towards different directions. And this is completely consistent with our variance bond because along each direction, at most epsilon fraction is deviated. So now let's try to run hyperplane carving algorithm on this example. So I first start by finding all the points that are non-trivially correlated with center of cluster mu1. These are all the points that are towards right of this hyperplane because all these points have large correlation or large dot products with mu1. So I find all these points and I remove them. Then I find all the points that are non-trivially correlated with center of cluster C2, that is mu2. I find them and remove them. And now it's the time to remove the last cluster. By that time, we already removed epsilon times k fraction of the vertices inside the last cluster when we were removing the previous ones. Like you see that we are removing some green points at each step, like epsilon times size of the last cluster at each step. So when it's the time to removing the last one, already epsilon times k fraction of that is removed. So then with this approach, we cannot prove guarantees better than epsilon times k misclassification error. But that is too bad for us because if epsilon is a constant, then epsilon times k might be too large. Like this works only if epsilon is much smaller than 1 over k. But we hope to get epsilon to be close to a constant. So then to fix this algorithm, we need to update the definition of candidate clusters to make them non-overlapping. To update this definition, now I define the candidate cluster C I hat as all the vertices that they have large correlation or large dot product with a specific cluster center, and they have a small dot products with all the other centers. And now by definition, the candidate clusters are non-overlapping. For example, you see that in the picture, these green points that they are like far from the cluster center C3 hat. So these are the points that they have large correlation with two different centers. These are the points that they have large correlation with mu1 and also with mu3. And now by definition of candidate cluster, now these points are not part of neither of the candidate clusters because they have large correlation with two centers. But for us, a candidate cluster contains only the points with large correlation with only one unique center. So now with this update, the candidate clusters becomes non-overlapping. So now we need to start by removing them. So one important feature of the problem is that when our graph is K-clusterable, then any collection of sets with outer conductance smaller than epsilon also has epsilon misclassification error with each cluster. Like for example, if I am able to find K set S1, S2 until Sk, and I show that these K sets have a small outer conductance epsilon, because my underlying graph is a union of K expander with outer conductance at most epsilon, it is not too hard to show that these K sets overlap a lot with the actual clusters, like the symmetric difference of S and the correct clusters is at most epsilon. So then our goal is to find k clusters with outer conductance smaller than epsilon. And it's not too hard to show that they provide a small misclassification error. So because of this lemma, what we do is that we define candidate clusters to be non-overlapping, and we remove a candidate cluster only if it has outer conductance smaller than order epsilon. For example, in this picture, we see that C1 hat and C2 hat both have outer conductance smaller than epsilon, because all the vertices in those clusters are very good concentrated inside them. So you do not have too many vertex outside. But you see that the last cluster, C3, has outer conductance larger than epsilon, because at least half of the points inside the clusters are not outside. So you have a lot of, because that was expanded, the cluster C3 was an expander, so you have a lot of edges going out of this candidate cluster. So that is not good for us. So what we do is that we only remove those candidate clusters that have a small outer conductance, and we proceed. So then our algorithm proceeds in stages. In the first stage, we start by all the centers. So in our example, for example, mu1, mu2, and mu3. And then we define all the points that they have large correlation with only one of these centers to be the candidate cluster. Then we estimate the outer conductance of each candidate cluster, and we remove the points that they have a small outer conductance. So it means that we can remove C1 hat and C2 hat. But now we need to proceed. Now we need to somehow find another technique that let us recover C3 completely. We cannot recover C3 here now, for example, because most of the points are outside. Then what do we do next is that we project out the direction corresponding to the removed clusters. So we project out the direction corresponding to mu1 and mu2. And it means that this is kind of equivalent of projecting all the other vertices onto direction of mu3. So it means that now I project all the other vertices on direction of mu3, and you see that the green points that they used to be outside, now all of them are concentrated on C3, because there is no other direction to be abnormally deviated towards that. So now I repeat the algorithm here. Again, in the new subspace with the lower dimension, I define a candidate cluster as set of all the points that are non-trivially correlated with one of the remaining centers, and I remove this if it has a small outer conductance. And you see in the picture, this happens because not all the points completely get concentrated. So the main idea behind this algorithm is actually use of subspaces. Because the points that they have abnormally large norm, and that was because they were correlated with many different directions, these points suddenly disappear when you project them onto a subspace with large dimension. And this is because the variance bond that I showed you at the beginning cannot concentrate on the subspaces. So because of this, we can show that at each iteration, at least half of the clusters can be recovered. And the other key idea is that not only cluster centers are orthogonal in the original space, but also after projecting out some of the centers, the remaining centers also remain orthogonal in the subspace. So putting these two facts together, we can show that at least half of the clusters can be recovered at each iteration, and it means that at most in log k iteration, all the clusters can be recovered. And that's where I get epsilon times log k in my misclassification error, as opposed to epsilon. That's where that log k comes from. And note that this algorithm has sublinear runtime because, first of all, computing dot products between points and dot products between points and centers can be done in sublinear time using the data structure we developed. And also, we can compute the projections in this spectral embedding in sublinear time. So it means that, like, when you look at the definition of candidate clusters, both terms, like the terms that you compute the dot product, the term that you compute the norms, and also when you compute the projections, all of these computation can be done in sublinear time. So the whole algorithm has nearly sublinear runtime. So this is the main idea of the clustering algorithm. Please let me know if you have any question about this.
Well, I have a small question. So you mentioned solving an issue with at the picture and the example we have seen that one of the clusters was well, not that concentrated, that there were multiple dimensions. I was wondering, would the same problem be at least to some extent solved if you would consider cutting off these clusters in a random order? Because you showed us example that if you start from removing the blue and red, then it cuts off the green part. But if you started removing green, this would be a solved problem. So
yes, that is true. That is true. But the problem is that, like, this is kind of an extreme example that we assume that all the abnormal points belong to one cluster. What if, for example, instead of doing this, you have a square root of k bad clusters such that each contains a square root of k epsilon, a square root of k times epsilon error. In that case, even if you do it randomly, you might get some bad cluster at each iteration.
Okay.
So it is actually crucial to look at subspaces, because in that case, these bad points won't exist anymore. But we actually believe that these examples cannot happen. I mean, we believe that it might be possible to show that this hard example cannot exist. But I think it is very hard to prove such things. Like, I can maybe show to you some of the hardness of why this cannot exist when I'm talking about the data structure. But it depends on how.
If you could prove something like this, could you like, then algorithm is faster, right? Or it's not?
So it won't get faster because you still need to do the dot products, and for that you need time roughly a square root of n. But the advantage of proving such thing is that you don't get that log k factor in our assumption. Like, we need to assume the outer conductance epsilon is smaller than 1 over log k, and we can misclassify epsilon times log k fraction of vertices. That's our main result. If you can prove such examples do not exist, you can even show that you can prove epsilon misclassification error, and for epsilon being a constant. So that's the advantage of showing such things. But we believe, I think it is hard. Like, we tried for a long time, but that might be hard. So I can go over the ideas of the data structure of computing dot products, or I can spend more time on answering questions on the clustering algorithm based on how much time do we have. So what do you prefer?
This is really up to you.
Okay, so maybe I can quickly go over the main ideas of the dot product oracle. So recall that our goal was to be able to estimate the dot product between spectral embeddings in sublinear time. So let u1 through un be the eigenvectors of the normalized Laplacian, and lambda1 through lambda n be the eigenvalues. Then, because our graph is k-clusterable, most of the properties are of the spectral embedding and most of the properties of random walk are mainly determined by the bottom k eigenvectors. So, and we recall that we were defining the spectral embedding of each vertex as a vector in Rk whose coordinates are ui of x. And recall that our goal was to estimate the dot product between fx and fy in sublinear time. So if we try to look at this carefully, this is nothing but the sum of the bottom k eigenvectors ui of x dot ui of y. That's what we hope to compute in sublinear time. And what is the main tool that we have? Like, as we see in the result by Schumacher-Staller, the main tool that we have to run algorithms with sublinear time is to run random walks and to estimate the L2 norm distance, or the dot product between the probability distribution of random walks. For example, because of birthday paradox, one can show that we are able to estimate the dot product between probability distribution of random walks, like m to the t times indicator of x and m to the t times indicator of y, with very good approximation, roughly n to the minus 1 minus epsilon, in nearly square root of n runtime. So if we look at the dot product between the probability distributions, this is nothing but the dot product between spectral embeddings that is distorted by factor 1 minus lambda I to the 2t. And recall that the whole problem in our setting was that when we get these distortions, we are unable to cluster the graph because the point clouds get, like as we have seen at the beginning of the talk, the point clouds get they are not as separated enough that we be able to classify them, as you see in the right picture. So our goal is to remove this 1 minus lambda I to the t when we are computing the dot product between the probability distribution of walks. So now let's look at the properties that our graph has. Because our graph is k-clusterable, we can show that the kth plus 1 eigenvalue is a constant. And since the length of the random walk we run is logarithmic, this factor 1 minus lambda I to the t will be exponentially decay for the terms larger than k, like starting from k plus 1 minus lambda I to the t, you can think of it as n to the minus 100, for example, and that won't matter. So then it's only the first k terms that we need to work with. So then let's again recall, our goal is to estimate uix dot uiy, sum over the first k terms. But what we can estimate is uix dot uiy that is distorted by 1 minus lambda I to the 2t. To remove this distortion, what we do is that we inject another matrix in the middle that cancels out the contribution coming from the eigenvalues. We basically try to construct this matrix, sum of ui transpose times 1 minus lambda I to the minus 2t, to cancel the contribution coming from the eigenvalues. But the problem is that this matrix that we need to inject the actually appropriate linear transformation that we need to inject in the middle is a very large matrix, and we cannot compute this large matrix in sublinear time. This is an n by n matrix. So then instead of this, we need to approximate this large matrix with a sparse low rank matrix. For this, this is what we do. So we sample a small number of vertices from our graph, and then we run random walks of logarithmic length out of each vertex, and then we construct the n by s matrix whose columns are probability distribution of random walks started from these vertices. So I have n to the epsilon vertices sampled in our graph. Like these are the columns you see in the picture, u1 until us, and then for each column is the probability distribution of random walk started from one of these sample points. So this gives me an n by s matrix, and I call this m to the t times s. So now after that, for any pair of vertices in the sample set, I compute the dot product, the collision between the probability distribution of random walks started from the sampled nodes. This is nothing but looking at m to the t times indicator of x and m to the t times indicator of y. And recall that it's possible to compute such collisions in roughly n to the half plus order epsilon because of birthday products. So I can compute this small s by s matrix whose coordinates are the probability that these two random walks collide. So after computing this small matrix, I just compute the eigen decomposition of this small matrix, and then I try to invert it and inject that inversion in the middle. And then we can show that if you do these algorithms gives you a very good approximation of the appropriate linear transformation that you need at the beginning to cancel out the contribution of eigenvalues. So the proof relies on strong matrix perturbation bonds such as Davis-Kahan, and also another important lemma that we use to prove this algorithm is that we can show that when the graph is k-clusterable with outer conductance smaller than epsilon, then if we look at any of the bottom k eigenvectors, u1 through uk, then the n infinity norm of any of these eigenvectors is bounded by n to the epsilon divided by a square root of n. Note that it is not too hard to see that on average, because these eigenvectors are orthonormal, ui of x for any x is on average 1 by n. Ui of x squared on average is 1 by n. And we can show that it is not too far from the average. It only can be more than n to the epsilon times the average. So, and this is crucial to prove that we get good enough concentration by doing this. So I hope that I can give some ideas on the data structure that we developed for estimating dot products in sublinear time. And let me stop here. Please let me know if you have any other questions.
Thank you.
Thank you.
So if I understand correctly, basically to work on something like this, you need to have a good intuition of how these things work in the spectral domain.
Exactly.
Right?
Yes.
This is like the main ingredient from the intuitive point of view, right?
Yes, yes. Like the fact that the graph was k-clusterable was important for both results. Like for the first result, for the clustering result, the fact that the graph was k-clusterable, for example, was useful to show that the centers are orthogonal, or the variance bond we show is based on the fact that the graph is k-clusterable and all those techniques. And also in the other result, on the result that we estimate the dot product between spectral embeddings, we use the fact that the graph is k-clusterable to show that L infinity bond, like the L infinity bond that I showed to you at the end. So this bond only holds when the graph is k-clusterable. And it is crucial to have this to show that the algorithm runs in sublinear time.
Do we know anything about some lower bounds? Let's say, why do we have I understand why do we have square root of n here, and it seems, if I recall the previous results correctly, this looked like a theme, there was this square root of n everywhere. Do we know if possibly if it's possible to go below that?
So actually, that's one of the main results we had on the last work. You see, Chiplunkar Kapral of Hana with Hana and Press. So there, the result there is also, there is a lower bond that we show there, and it is not only for clustering, but also even for property testing regime, you need that lower bond. The result is like this: that even if you want to distinguish between a graph that is k-clusterable and the graph that is epsilon far from being k-clusterable, you need to run at least n to the half plus omega epsilon query. You cannot go below that, even for testing.
Okay. Yeah, and this is even for constant outer conductance, right?
Even for constant,
yeah.
Yes. But note that, for example, when epsilon is smaller than 1 over log n, this n to the epsilon become a constant, and that matches the previous result. Because the previous result has only a square root of n runtime. But these two match because for epsilon is smaller than log n to the epsilon is a constant.
Okay. Thanks.
Let me also talk about one important, maybe interesting open problem on this result. The main clustering result that we have, the query time is exactly sublinear n to the half plus order epsilon. But in the pre-processing time, we have exponential dependency on k and epsilon. And this exponential dependency comes from the fact that we need to first guess the position of cluster centers. And after guessing, we assign the points by doing that hyperplane partitioning. So for that guessing, we need to go over roughly 2 to the poly k number of guesses, and that's why we get this factor, and it's very interesting to remove that as well.
I have one question.
Mm-hmm.
I was wondering, is there a chance of relaxing this assumption on the graph being k-clusterable in the following direction? So I can imagine instances that would have some clusters clearly outstanding, say k-half such clusters, and then say the remaining vertices less clear if they should be apart or together. Could you imagine constructing an algorithm that would be correct on those distinguishable clusters, but could possibly make arbitrary errors for those parts that are that you don't have any structure there?
I see. That's actually a very nice direction to consider. There is one recent result by Pang, who actually considered doing the clustering in the noisy regime, where you can have some clusters, as you said, that are somehow outstanding. They are expanders with a small outer conductance, but you may have like some other vertices that are somehow, you don't have any structure for them. And you still would like to recover the clusters with the existence of the noise.
So you say that there are some works on that?
Yes, there are some works on that, and like most of them are still in the regime that the outer conductance is smaller than 1 over log n. Like it is even interesting to explore that setting, even for a small outer conductance. Like.
Thank you.
Okay, let me stop the recording for now.
Sure.